Consider the following integral. We'll look at the integral of 3 over x plus 3 minus 2 over x minus 1. Okay, so we should be able to integrate this. We have two basically fractional terms. They're rational expressions with an x in the denominator, but the natural log will work here, right? So the first one would simply be 3 times the natural log of x plus 3. We get minus 2 times the natural log of x minus 1. Right, I mean, and then the plus c. So it works, seems straightforward, but there's something that's kind of really interesting about this. And what's interesting is that if you look at it in terms of combining the fractions, so this is the same as if we subtract these, we've got 3 times x minus 1 minus 2 times x plus 3, and that is all over x plus 3 times x plus 1. And certainly you could multiply out the numerator, okay? And if we do that, we end up with, let's check this. We've got 3x minus 2x, that's just an x. And then we've got negative 3 minus 6, that's negative 7. And so we get x minus 7 over x plus 3, x plus 1 dx. So what we have here is that if you start with this integral and you reverse this process, the correct answer is right here. And the way you discover that correct answer is through splitting the fractions into 2 and then sort of figuring out what these numbers would be. And this is precisely the method that we actually want to look at, okay? It's called the method of partial fractions, okay? Sort of a big method, and let's take a look at an example. So what if we want to integrate the following? How about, and we'll do something that's kind of similar to this, okay? Let's consider, one other piece I should mention here is that the denominator can also be multiplied out. And so if we look at this, this is also the same as x minus 7 over x squared plus 4x plus 3. Right, so that's kind of interesting because this is typically what you are actually going to start with. Okay, so let's consider something similar. How about x plus 7 over, let's go with x squared plus x minus 2 dx. Okay, so this is what we're trying to integrate. And the idea is we want to use this method of partial fractions to figure it out. And we're going to learn the method through this example. So the first thing you want to do certainly is to factor the denominator. Because if we factor the denominator, and we can just leave the numerator as is for now, but factoring the denominator will give us, okay, what do we have here? We've got an x and an x to get the x squared, and then we need a 2 and a 1, and the 2 should be a plus to make it positive. Okay, so now we factored it, and the idea now is we want to split it, okay? And we're going to split it, and so what we want to do is something like this. We want to say, okay, we don't really know what the term is for the x plus 2. And we don't really know what the term is for the x minus 1. But we do know that when we combine them together, we're going to get x plus 7. Okay? So this is sort of the method. You factor the denominator, and then you split it into unknowns in the numerator, and then you go through and you do the algebra, okay, meaning now we're going to put them together and see what A and B sort of look like. So if we combine these together now, it's going to be A times x minus 1. It's just standard adding fractions. Plus B times x plus 2. And this is going to be all over x plus 2, x minus 1. See, we're not changing the denominator, okay? What we're changing here is we're, A and B, we're figuring out what they are. Now, if we keep going, I'll write this out in, so here's what we have. We have ax plus bx, okay? So I'll write this out. And so you can write that as a plus b times x. And then we have negative a plus 2b, right? And then so we have, could write that as, let's just write it as minus a plus 2b, okay? I mean, you could write it as plus, it's like simply two terms, the negative a plus 2b. And what we have, in effect, that's times 1. What we have here is that we have these single terms, sort of the a plus b. A plus b, that's the coefficients in front of x, must equal 1, okay? So what we have here, we know that a plus b must equal 1. Additionally, 2b minus a, okay, or you could write it like this too, negative a plus 2b, sort of like becomes a system with two equations with two unknowns. What does this equal? It must equal 7, okay? And so we really have two equations with two unknowns. We need to solve for a and b. And plenty of ways to do this. You can just add these straight down, and we get 3b equals 8. So we get b equals 8/3. And if b equals 8/3, then a must be negative 5/3 to give us the 3/3, which is 1. Okay? So b is 8/3, and then a must be negative 5/3. Okay, so that basically does it, because now when we say we keep going with this problem, if we look right here now, okay, we've just said, well, a is negative 5/3, right? So, you know, you could just write it up there. Negative 5/3 over x plus 2. And b is 8/3 over x plus 2. Sorry, x minus 1. And that's what we want, right? Because now we can actually integrate it, right? So if we integrate it, it's just these times the ln's. You can pull out the constants. So it's negative 5/3 natural log of x plus 2, and this is plus 8/3 natural log of x minus 1 plus c. Okay, so that's the method of partial fractions. Okay, there are different layers to it. I don't know how much we want to get into all of the layers right now, but I will say this. It's helpful to know like when you do and don't need it, okay? So let me just show you a couple examples of when you don't need the method. Here's one you could consider. What if you had, say, the following? You have the integral, and then you've got x cubed plus x over x minus 2 dx. Okay, why is this not a partial fractions? So actually, if you have the numerator as a higher exponent than the denominator, then you could try long division. And so if we do long division here, okay, so what's the long division? The long division would be We've got x minus 2 going into x squared, x cubed plus 0x squared to help keep track of it plus x. And then we just say, okay, well, how many times does x go into x cubed, x squared times? And then we multiply out, and we get x squared times x is x cubed. Then we're going to get the minus 2x squared. So we subtract, and then we get that's a plus 2x squared. And you bring down your next term, which is plus x. Then we do the division again. So how many times does x go into 2x squared, where it's plus 2x times? So now we get the 2x squared, and then we get the minus 4x. And when we subtract here, we get, subtracting makes it positive, and so you would get a positive 5x. There's nothing else to bring down. You go one more time and do the plus 5. And so now we get 5x minus 10. I mean, if you like, there's a plus 0 here. And then you subtract those, and here you're going to be left with a remainder of 10. But the way you write that is plus 10 over x minus 2. That's how you write the remainder. And so what's nice then is now you can, that rational expression equals what's right here. Okay, so this is the same as, put it over here, the integral of x squared plus 2x plus 5 plus 10 over x minus 2. All dx. And now it's easy to integrate this term by term. We get x cubed over 3 plus x squared plus 5x plus natural log of, well, 10. We got to put the 10 in there first. It's not natural log of 10. We're just pulling out the 10. Limits, integral sum of limits, so you can pull it out. 10 natural log of x plus 2. Sorry, x minus 2, and then we got the plus c. And then you have it. Okay, so that's an example of one where you don't have to use the, you shouldn't use partial fractions, because it's not going to work. Partial fractions are when the numerator has a lower power than the denominator. And that's basically it, although I will show you maybe one more sort of like non-example. So what's another sort of non-example here? A non-example, meaning where you don't use partial fractions, be the following. So what if you have x, say, plus 1 over x squared plus 4? All right. Why not? Okay, how are you going to factor the denominator? Ooh, issue. So this one, what you would do is you would actually sort of separate it out into x over x squared plus 4, and then 1 over x squared plus 4. And you would treat these separately. And so to do these separately, okay, well, the first one, it's good, because you take the natural log of x squared plus 4, you get 1 over x squared plus 4 times 2x. There's no 2. Okay, so the 2 would cancel out with the 1/2. And the second one is actually a special form. It's the tangent. Okay, so the tangent inverse. The derivative of tangent inverse of x is 1 over x squared plus 1. And when you have the form like this, it's considered x squared plus 2 squared. And what you do is you put 1 over the 2, and then it's tangent inverse of, and then you get the x over 2. Okay, so we just went over a couple of examples of where you wouldn't use partial fractions. Whenever you do use it, it's a standard technique. And I do want to highlight too maybe a difference. Like, why can't you do natural log here? Well, by the chain rule, you're going to get 2x plus 1. It's just not going to match well. So those work when you have a single term. when you have more than one term, you want to split it off into two different, or more, it could have more, okay? You want to just factor it. You could have this third term, a c in there, and then you split it out and you just say a over the first term plus b over the second term plus c over the third term, okay? And then you combine it, just add your fractions like regular, but you've got an a and b in there. So if you separate like the x terms together, the single terms, like the ones together, you may have some x squared terms together also. And instead of solving a 2 by 2 equation when there's a c involved, you could solve a 3 by 3 equation. But you solve for a, b, and c. You put it back into the original like we did up here, and then they should become straightforward logs to solve. I should say to integrate. Logs to integrate.